Welcome, everybody. It's my pleasure today to introduce Francisco Martinez, and he'll be telling us about the chromatic number of G-Borsuk graphs.
Good afternoon, everybody. Thank you, Henry and Facundo, for the invitation. So I'm going to be talking today about this project. So just as a quick introduction, let's remember that a graph is a collection of vertices and a collection of edges, which are unordered pairs of vertices, U, V. In a graph coloring, a K coloring is an assignment of colors from 1 to K to the vertices of the graph in such a way that if two vertices are connected by an edge, they are assigned a different color. Then the chromatic number of a graph is going to be the minimum K, such that we can find a K coloring of that graph. In general, computing a chromatic number of a graph is hard. It's actually an NP-complete problem. So we like to have bounds for them, and finding an upper bound basically means actually finding an explicit coloring. But finding lower bounds, well, you have to prove that you cannot use less colors than whatever color the chromatic number, whatever number the chromatic number is. So it's harder. So the motivation to our study comes from this problem, the Kineser graphs. So the Kineser graphs are a family of graphs parameterized by two parameters, n and k. The vertices are the k subsets of the numbers from 1 through n, and the edges, we draw an edge between two of those k subsets whenever their intersection is empty. So some examples, the ubiquitous Peterson graph can actually be seen as a Kineser graph 5,2, meaning that the vertices are pairs of the numbers from 1 through n through 5. And the complete graphs actually are also examples of Kineser graphs where the second parameter is 1. So given an explicit color on if this class of graphs is not hard, we can color the vertex f by the minimum between the minimum of f and n minus 2k plus 2. And this happens to give a n minus 2k plus 2 coloring. So we know that the chromatic number is bounded above by this number. And the conjecture that comes since Kineser's time in 1955 is that this is actually the chromatic number. And it was finally proven by Lovash in 1978. So it took a lot of time to prove this statement. And the reason is because Lovash's proof is actually revolutionary, and the idea that he used is that he used topology. So more or less the idea of those kind of proofs is the following. We can start with the graph. Then to that graph, we correspond a simplicial complex. In this case, Lovash introduced the idea of neighborhood complex. Then he looked at the connectivity, which is a topological property of this simplicial complex. And that connectivity is the one that gives the lower bound to the chromatic number. So the definition of this neighborhood complex that he gave is just that it is the simplicial complex where the vertices are the vertices of the original graph H. And the simplices correspond to subsets of vertices such that those vertices share a common neighbor. And then he was able to prove that the connectivity of this space, and by connectivity we mean the maximum K, such that all the homotopy groups up to order K of this simplicial complex are 0. Plus 3 is always a lower bound to the chromatic number of H. Then he computed this connectivity for the family of Kineser graphs, given the n minus 2k minus 1. And then by adding 3, we have the lower bound that we needed. So in this case, he introduced a topological way of finding lower bounds to a chromatic number of graphs. And he also showed that this topological lower bound is efficient for Kineser graphs. So a natural question to ask is, okay, we now have this topological lower bound and we know it's efficient for Kineser graphs. How effective or how efficient is it for random graphs? We can, of course, talk about the Erdos-Renyi random graph as a model to test this. The order-randy random graph, let me remind you, means that we have n vertices, and then for each pair of those vertices, we add that edge with probability p, independent from all the other edges. So what Matthew Kale was able to prove is that actually the connectivity of the neighborhood complex of these order-rangy random graphs for some parameters p, if the parameter p is like this, then it is actually bounded above by a constant. And if the parameter is 1/2, it is bounded above by a function, logarithmic function of n. But in either case, the actual chromatic numbers of these graphs are understood, and they are known to go to infinity faster, way faster than these bounds. So at least this topological bound seems to be not efficient for this model of random graphs. So the next question we can ask instead is, okay, can we instead define a different model of random graphs where topology is actually somehow effective? Any questions so far? So we look at this model of Borsuk graphs. The Borsuk graph, the original Borsuk graph is like this, given a dimension d and some parameter epsilon positive. The d-dimensional Borsuk graph is a graph that has as vertices the whole unit sphere, SD, and where we're going to join edges if the distance between x and y is at least pi minus epsilon. So this is the geodesic distance over the sphere, and saying that 2 points are at a distance at least pi minus epsilon means that they are almost opposite to each other, almost antipodal to each other. So why is it called like that? It's called a Borsuk graph because it has to do with Borsuk and Borsuk-Ulam theorem. And let me remind you that the Borsuk-Ulam theorem tells us that there is no C2 map from the n-dimensional sphere into the n-1 dimensional sphere. In other words, that means that there's no continuous map that goes from the n-dimensional sphere into one dimension less, satisfying that it is an odd function. So the chromatic number of these Borsuk graphs where the vertices are the whole unit sphere for epsilon small enough is exactly d plus 2. And what is interesting is that actually this chromatic number, this theorem is equivalent to the Borsuk-Ulam theorem. And the easiest way to see that they are equivalent to each other is by looking at their equivalence to the other theorem, Lusternik-Schneemann-Borsuk theorem. So let me tell you about that theorem. So that tells us that for any closed or open cover with d plus 1 sets of the d-dimensional sphere, there is at least one set of them containing a pair of antipodal points. So we use that as the lower bound for the chromatic number of these Borsuk graphs. And the upper bound, we have to realize an example. So that can be done in these ways. The d plus 2 coloring can be realized by projecting the faces of the d plus 1 simplex. So for the one-dimensional sphere, we project the faces of a triangle. And for two-dimensional sphere, we project the 4 faces of a tetrahedron, etc. And we see that they agree with each other, so that gives us the chromatic number. So we can actually randomize this construction and get a model where topology tells us something. So randomization is pretty easy. Instead of taking the whole sphere as the vertices, we take n random points on the sphere. And still we're going to connect 2 of those vertices with an edge if their distance is at least pi minus epsilon. So these are a couple of examples. And what we were able to prove is that there exists some threshold for epsilon depending on n, such that with high probability as n goes to infinity, the topology gives us the same chromatic number that we saw for the whole Borsuk graph. And if we're not within that region, then the chromatic number might be less than that. So this is the one theorem that we were able to prove. If epsilon is greater than some constant times log n over n to 1 over d, then asymptotically, almost surely, the chromatic number of this random construction is still d plus 2, which was the chromatic number of the whole thing. What if epsilon is smaller than a constant times that threshold? Then asymptotically, most surely the chromatic number is actually less than that, at least at most d+1. So that was one way of thinking about this problem. But then what we thought about is there any way in which we
Francisco,
can...
can I interrupt with a question?
Yes, of course.
Yeah, so I'm just trying to, okay, so you have all edges that are least pi minus epsilon, right? I see. So as epsilon is getting larger, you're having more and more edges.
Yeah.
Right. So for epsilon larger, that's why, the chromatic number might be higher. Okay, I'm with you.
Thank you.
Thanks.
Yeah, so I'm thinking right now of epsilon as a function of n, and n is the number of vertices. So as the number of vertices increases, of course, we'll have more edges, but also the condition of when we draw edges is easier to satisfy, or harder to satisfy, actually. Yeah, so as epsilon goes to 0, we'll have less edges, but we'll have more vertices, so that makes this work. So we're thinking, is there a way in which we can generalize these ideas to other kind of spaces other than spheres? And what we realize is that the antipodality is actually a C2 action, and this property that x and y is greater than pi minus epsilon is the same as saying that x and minus y are within epsilon distance. And just by realizing in this very small different way of thinking about this, now we can realize these ideas if we have a different action. For example, if we have a C3 action over a circle, which could be just rotating the circle by 2 pi over 3, then we can connect edges between x and all the points that are close to nu of x, but also between x and all the points that are close to nu square of x. So using this way of thinking, we can extend this idea to other spaces where we have G actions, at least for any finite group G. So we can define what we call a G-Borsuk graph or generalized Borsuk graph. If we have G a finite group, suppose K is a free geometric G simplicial complex. I'm going to explain that in a bit, but basically that means that we have a G action on that space. And if we take a subset of points in that set and epsilon greater than 0, then we can define the G-Borsuk graph on those vertices, on those points, with epsilon as follows. The vertices are that set of points, and then the edges, we draw an edge between x and y. If there is some element in G that is not the identity, such that the distance between x and G of y is at most epsilon, or the other way around, G of x and y is at most epsilon. So these are a couple of examples. Now we can, if we have a C2 action on a torus, on a 2 torus, we can define a G-Borsuk graph on them. But also if we have a C3 action in, say, a circle, we can define a Borsuk graph in there. And of course, this is a generalization, because if we look at C2 actions on the sphere, we get back the Borsuk graphs. So I'm talking about G simplicial complexes, so let me tell you what that is. We say that a simplicial complex is a G simplicial complex if the group G acts on K via simplicial maps. And we are mostly interested if the action is free. What that means in this context is that for every face of K, the face and the orbit of that face have an empty intersection. So sigma intersects G of sigma for any non-unity G has to be empty. We are going to talk about a geometric simplicial complex, and that simply means that we have a geometric representation of this space, and we are thinking of that as a geometric object. So of course it has topology, but it also has distance, it also has volume, and we are already given that. When we say we have a geometric simplicial complex, we are given all of this geometric structure. A G map is going to be a map between G simplicial complexes that respects the G action. So it's an equivariant map. The way in which we're going to think about these G simplicial complexes as metric spaces is by using the shortest path distance. And for this talk today, we consider all our geometric G simplicial complexes to be free and such that G acts via isometry, just to make the statements a little bit easier.
And when you say shortest path distance, each simplex is sort of the standard Euclidean simplex where all edges have the same length, like maybe 1 or something.
Yes. Yes. We're thinking about triangles and tetrahedra in Rn, and then to go from one point to another, all the paths are going to be piecewise linear because you're going to move from one simplex to another simplex, and in each simplex is just a line segment.
Thanks.
Okay, so if we're talking about G spaces, we also need to talk about G index. So when we have C2 actions, it is natural to use spheres because spheres have a natural C2 action, which is the antipodal action. And let me remind you that spheres can be seen as simplicial joints of the space C2 times C2 D plus 1 times. When I say C2, I'm thinking about 2 discrete points. Okay, so taking D plus 1 times a simplicial joint of 2 points is going to produce the D-dimensional sphere. So a similar construction can be made for general groups G. Simply take the group G, and by taking the group G, I mean, suppose the size of G is M, so that means we have M discrete vertices. We identify them with G because that gives us an action, a trivial action, but just right or left multiplication. And so we are going to define these EDG spaces as taking the simplicial joint D of plus 1 times of this space G. So they have a G action that is given by, let's say, left multiplication of G on each of the coordinates. We can think of these spaces as D-dimensional approximations to a classifying space, and if you know what that means. And once we have this definition, we can define the G index to be the minimum integer D, so that we can find an equivariant map or a G map from X into this EDG space. Okay. So it turns out that this definition makes sense. The theorem, and this is not my theorem, this is already done, is that if you have a G map, then the G index of X is less than or equal to G index of Y. Now, this is well defined because the G index of the D space G is exactly D. And this statement actually can be seen as a generalization of Borsuk-Ulam theorem, or actually this is Dolt, or depends a lot on Dolt's theorem, that there are not G maps from the D-dimensional classifying space into the D-1 dimensional one. And we're going to use this property that if K is a free simplicial G complex of dimension D, then its G index is at most that dimension. Okay, so in the original Borsuk graph case, we had Lusternik-Schindelman-Borsuk theorem. We would like something similar in this setting, but we don't have that yet, so we can define that number in this way. The G covering number of M, if M is a G space, is going to be the minimum case so that we can cover M in K open or closed sets, such that UI intersection GUI is empty for each I and for each G. Okay. And of course, we can talk about this because this covering number and the chromatic number of the G-Borsuk graphs are actually the same thing. If the epsilon is small enough, and we take a subset of the simplicial complex that is a net that covers that it is sufficiently dense on that space, then the chromatic number of the corresponding G-Borsuk graph is equal to this G covering number. So this is actually a pretty easy theorem, but this is the duality that we use to be able to prove bounds on this number, because what we care about is about bounding this number, the chromatic number, and we will use this duality to be able to bound that.
Francisco, can I interrupt again?
Yes.
Yeah, so I'm just trying to parse this. So the case, G is Z mod 2, and it's acting antipodally on M, which is the N sphere, right? So this condition of the covering number, this is sort of the minimum number of closed or open sets you would need so that no set contains antipodal points. Is that right?
Exactly.
Okay. And then if this theorem, you're saying, I see. So, okay, from a dense enough sample, what's K? Oh,
yeah, G simplicial complex. Sorry.
I see. Okay, so for for a dense enough sample of a G simplicial complex, the covering number of that G simplicial complex is the chromatic number of the Borsuk graph. Okay, cool. Thanks.
Yeah, thank you for asking. So just to make our notation a little bit easier, whenever I talk about the G covering number of the D-dimensional G classifying space, I'm just going to write cov G of D. And well, actually, the construction that I showed you for these spaces is not the only construction that we can have. So this property actually makes sense because this number is going to be the same for any possible construction of this kind of sets of spaces. So what we care about is about bounding this number, and this is what we were able to give as bounds.
Sorry, one quick question. Could you
Yes.
go back to the previous slide? I just wanted to look at the definition of cap GM. 1 second, please. Infimum K. Okay, thank you.
Yeah, thank you. Okay. So again, this means that what is the minimum number of open sets we need to cover the space such that applying the action on each of those sets, it doesn't intersect the original set. So these are the bounds that we were able to give. Lower bound, the size of G plus the dimension, and upper bound, D times G minus D plus 2. So you can see that these bounds are both linear in D, linear in G, but sadly they are far away from each other. In the particular case where G equals C2, so the size of G is 2, both bounds that we give here are the same, and we have just D plus 2. So the lower bound is a LSB theorem, and the upper bound is that construction of covering with the facets of the simplex, of the regular simplex. This lower bound that we give here, that is where we use the topology that I want to describe. And the upper bound, maybe we'll discuss a little bit, that is an induction construction. So this lower bound actually also gives a corollary that looks like the LSB theorem. If we have K a finite G complex, a free G complex, which is deconnected, and the size of G equals M, then if we cover K with D plus M open or closed sets, then there will exist some I and some G, so that X and G of X are on the same UI. So we have upper and lower bounds, but we would like to know the exact number. As I mentioned, when the group is C2, for any dimension, we know that the exact number is D plus 2. It's trivial to show that if the dimension is 0, then for any group G, the covering number is just the size of G. It's not trivial, but it's possible to prove that the dimension is 1. Then we again hit this G plus 1. And for these small groups, C3, C4, etc., in dimensions 2 and 3, we already had a lower bound. So what we did is that we found upper bounds that matched that lower bound, and that gave us the exact numbers for those. So in dimensions 0, 1, any group G, the lower bound is the correct chromatic number. For C2, the lower bound is the correct chromatic number. And for these small examples, the lower bound is the correct chromatic number. So we conjecture that this lower bound is actually the correct covering G number for any space. Again, this is a topological construction, and you saw that the construction of these spaces is very topological, so it does make sense that the topology gives a better result than this upper bound. This is still a conjecture so far.
Francisco, can I ask a question?
Yes, yes.
Yeah, this is very cool, by the way. So, covering G of D, that's defined as covering G of this sort of classifying type space EDG, right?
Yes.
And so for that, you're using this fixed construction, maybe the D+1 fold join of the group G with itself, I think.
Yeah.
You said previously that this is an invariant. What do you mean by that? Did you mean that, like, if you used a different construction of EDG, you get the same number, or?
Yes.
I see.
Yes, yes.
Cool. Fantastic. Thanks.
Yeah,
So
thank you.
I have a question too. Can I ask something?
Yes, of course.
Yes. So assume we know covering G of D and covering H of D for two groups G and H. Then can you say anything about the covering G product H of D?
There should be some kind of property like that. I don't have any results in that way, but
Okay.
yeah, of course, you know, if you have a G space and you have a subgroup of G that is also a subgroup H, then it's also a G space, and at least you have an upper bound of this G covering number. But that's the only thing I have so far. Yeah.
Mhm. Then sorry, what about if we know covering G of D1 and covering G of D2? Then can you say anything about covering G of D1 plus D2?
Oh. I don't know.
Okay, thank you.
Yeah. I imagine that a similar idea that what we use for this upper bound can probably give some bound in that case, but I don't have that.
Okay.
Thank you. Yeah, so as I was mentioning, we only have a very easy cases, the complete picture. For dimensions higher, we actually needed to find these colorings, and what we did is we actually found them on a computer. So and here is why I was talking about the case that we have different classifying spaces, because the classifying spaces that I'm using here are not exactly the joins. So here I have a classifying space of E2, dimension 2 of C5. And what I'm doing is giving it a 7 coloring, which is exactly 5 plus 2. And this is a proper coloring of that space. So the way in which you would understand this space is that all of these circles, you should think of them as identified by the boundary. And the C5 action here actually will rotate the whole big circle by multiples of 2 pi over 5. So the way you can check that this coloring is actually the coloring we want is that every time we do one of those flips, for example, if we rotate everything, we should see that this pink part over here will not intersect with the pink part over here or here or here or here. And that happens for all colors. And we have the same construction. The the largest group for which I was able to do this was for C6. Okay. So what was the idea of that lower bound that we are thinking should be the actual chromatic number of these spaces? So this lower bound, the idea to prove that goes like this. So we start with the G-Borsuk graph. We associate to that a topological space. In this case, we're going to use the Hom-complex, which is a proto-simplicial complex. I'm going to explain that in a bit. Then we compute the G-index of this space, and that's the one that gives us the lower bound for the chromatic number. So the Hom-complex, a graph homomorphism is a map between two graphs, such that if we have an edge in the original graph, then it maps that into an edge in the second graph. Okay, a graph homomorphism is a map that sends vertices to vertices and edges to edges. So in 2006, Babson and Kozlov introduced the idea of Hom-complex between two graphs. The vertices of this Hom-complex are graph homomorphisms between the two graphs, and they give a topological structure to this. I'm not going to explain the whole idea, but the cells of this topological structure are products of simplices. They were also able to prove that this is actually a generalization of the neighborhood complex that Loash introduced, because if we take the complete two graphs, so just an edge as the first graph, then this Hom-complex is homotopy equivalent to the neighborhood graph of H. And actually, you can find simplicial collapses and anti-collapses from one to the other. So we use this to prove the theorem. So let me remind you of the facts that we said. The Hom-complex between H1 and H2 is a CW complex, actually a proto-simplicial complex. It's not hard to compute the dimension of this space if we are talking about complete spaces between Km and Kt. Actually, Babson and Kozlov proved that this space is a homotopy equivalent to a wedge of spheres of this dimension. And if we have G, a finite space, a finite group of size M, then the space Hom, Km, and any other graph here is actually a free G space. And this free G action actually is functorial, because if we have a graph homomorphism between H1 and H2, then we get a G map between the Hom of KMH1 and the Hom of KMH2. Remember that there is always a graph homomorphism between a graph H and the complete graph size, the chromatic number of that graph. So construction is as follows. If we start with K as G simplicial complex with G index K, we will take a small triangulation of K, and then we construct H to be the G-Borsuk graph on the vertices of that small triangulation. So then we can prove this. The chromatic number of H is less than or equal to the chromatic number of the Borsuk graph of this space. And that is at most the G covering number of this whole space K. Then we have a G map between Hom Km and Hom Km, K the size of G, the chromatic number of H. And we have to build an equivariant map from this space K into this Hom-complex space. Once we do that, just applying the properties of the G index give us the bound, because the G index of K was K. Then that has to be less than or equal to the G index of this, because we have a G map. That has to be less than the dimension of this. And that dimension we know is at most kind of the chromatic number of H minus. So that gives the theorem.
Francisco, can I ask a question there?
Yes, thank you.
I was wondering if you could walk me through the very first step, why the chromatic number of H is at most the chromatic number of this Borsuk graph.
Yeah, there's. I think the problem here is that I'm not seeing what X is. So probably, so X is the vertices of T, and actually this is an equality. The chromatic number of the Borsuk graph H is the chromatic number of Borsuk G.
Right. So that's just the definition of H then, I guess.
That's just the definition, yeah.
Okay, I'm with you. Thanks.
Sorry.
No, no worries at all.
Yeah, so that is the lower bound. That's with these constructions are somewhat topological. Just to complete this idea, let me tell you what the proof of the upper bound is, although again, it's not a great upper bound. So the idea is to use a recursive formula that the G covering number of dimension D is almost the G covering number of dimension D minus 1 plus the size of G minus 1. If the conjecture was true, then we should be able to substitute this size of G minus 1 by just plus 1. So the initial case is to prove that this happens to be true for dimension 1. And the way in which we do that is by first looking at the cycles. The classifying space of dimension 1 of the cycles can be seen as just the circle where we have 2 pi over m rotations. Then if we divide that circle into m plus 1 segments of the same size, that is a covering of this space. And then that construction can be extended into a cover for every group G by using the joint construction and the fact that every permutation can be seen as a disjoint product of cycles. For the recursive step, what we do is that the d-dimensional G space is, by the construction that we gave, G simplicial joined with the d minus 1 dimensional G space. And this can be seen as G cones identified by the boundary. And if we already had a covariant of this boundary, ED minus G, then we can basically extend that boundary to the center as long as we give the center a different color, G minus 1 times, the size of G minus 1 times. So then if these apices have different colors, when we apply this action, which will rotate the boundary and move the disks around, the boundaries won't intersect on the same color by construction, and the apices won't intersect on the same color either because we gave them different colors, and completely new different colors. So finally, let me tell you a little bit about making the random G-Borsuk graphs in this case. So the same idea, but now we have a probability measure on a geometric simplicial complex. We can define a random G-Borsuk graph to be the graph where the vertices are n randomly chosen points according to the probability measure. The theorem that we have is for the uniform probability measure. What I mean by that is that for every measurable space A, that is going to be contained into some simplices of this space, into some d-dimensional simplices. So we just look at the dimension of that intersection over the dimension of the whole thing, if the dimension of the simplicial complex was D. Okay, so basically the most natural probability measure that we can have. So then if we have that probability measure on K being a geometric EDG space, and provided that epsilon goes to 0, then there exists constants C1 and C2 such that if epsilon is greater than this is the same as the G covering number. So in other words, as the whole thing, And if it is smaller than that, then asymptotically, usually the chromatic number is less than the G covering number, but one dimension less. Of course, again, the conjecture is that these numbers are different, but I don't have proof of that yet. In the case where G equals C2, we actually get back the original theorem that I showed you for spheres, but it's actually better because it actually works for other spaces, other C2 spaces that are not spheres. For example, a torus. And that's all I had for you today. Thank you.
Thanks so much. So before we get to questions, let's briefly unmute ourselves and applaud for Francisco. All right, questions for the speaker? Let me start with a question. So I'm putting two archive links in the chat. They're both archive links to papers that you're on. I just wanted to see, is it correct to say that the first paper I linked to generalized Borsuk graphs, that sort of corresponds to the first half of the talk, and then the second paper, the chromatic number of random Borsuk graphs, that of course corresponds to the random results you mentioned at the end?
No, actually the other way around. So the first one corresponds to a case of C2. So we only talk about spheres. And in this, so the second one, we only talk about spheres. And the first one is all of these G construction, both the non-random case and the random case.
Okay, great, thanks. Let me ask another question. So could you go to slide 17?
Can you see my slides?
Yeah.
Okay.
Yeah, perfect. So I was hoping you could walk me through this theorem in blue. So first of all, is this your theorem?
Yeah.
Okay, so yeah, so K is sort of this K is a G simplicial complex, right?
Mm-hmm.
Yeah, so yeah, could you help me? Why should I believe this chromatic? How can I see that this chromatic number should be equal to this covered number?
Yeah, so basically suppose, so we have, suppose, an epsilon over 2 net. So we have points that are very dense on that space. And suppose that they are, we have a chromatic number, we have a coloring of them in some chromatic number. Then if we use small balls around those points, we can cover the whole space. And then, yeah.
Small balls around each color.
Small around that cover the space, and then simply saying that all balls of color 1 are U1, or all balls of color 2 are U2, etc. That gives you a G covering. So that takes care of one of the directions.
Yeah, yeah.
And for the other direction,
you probably use the covering to define the colors.
Yeah, so I'm sorry, I'm definitely missing something here. So we need K to be compact.
Okay.
So if it is a finite simplicial complex, there's no problem with that. Because then, suppose we have a G action and we have a coloring of these spaces, then what we use is that epsilon should be the infimum of the distance between each of these and all of the orbits of that space.
I see.
And then for the colors, then for the colors, yeah, just give to each of the vertex the minimum color of whichever UI they are in. So yeah, it will be taken care by the fact that we choose the epsilon, such that that distance is the infimum, or actually smaller than the infimum between the distances of this covering.
Thank you so much. So there's a question in the chat from David. What is the case for the three-sphere? I'm speaking from the topological perspective. David, feel free to unmute yourself if you have more to say.
For the three-sphere, so that if we talk about three-sphere, then we're talking about antipodal action, I imagine. And then we can cover that with 5 colors. And if we choose random points on the sphere, and we can do a construction of a random Borsuk graph. And also if epsilon grows as the theorem, then the chromatic number should still be 5. Yeah, so this G covering number, what that means is that the minimum number of open sets in which we can cover that is three-sphere is 5, in such a way that none of those 5 open sets has a antipodal pair of points.
More questions? I'm going to be greedy and ask another question. Francisco, can you go to one of your early slides where you mentioned what's known about the chromatic number of the Borsuk graph of the sphere? I think for epsilon small. Yeah, perfect. So this theorem, chromatic number for epsilon small enough, the chromatic number of the Borsuk graph is d+2. So, right, this is you have all edges that are sort of within epsilon of being antipodal, roughly. Okay.
Yes.
So now let's say we increase epsilon, so we allow more and more edges. Okay. Is anything known about how the chromatic number transitions as you increase epsilon, allowing more and more edges? Like, like, is it known, or is there conjecture, what value of epsilon is now going to mean that you need d+3 colors or d+4 colors or more?
That's actually a great question. My personal conjecture is that would look like this, but the D will move around. So, yeah, but that's just a conjecture. We don't have that result yet.
But this is sort of, this is sort of with random points as epsilon's always sort of going to 0. Like the full sphere, you could ask, it's known that for small epsilon, you need at least d+2 colors, but, one might imagine that as you allow in more and more edges, the chromatic number is going to have to go up. And I'm curious if anyone knows when that transition first occurs, or then how fast the chromatic numbers increase.
Oh, yeah, I don't know. Sorry, but that's a great question. Yeah, that's a great problem to work on.
Any more questions? Well, if not, thank you so much, Francisco. A lot of cool stuff for me to try to learn a little bit more. And let me stop the recording here.
Thank you.